In this video, we're going to take a look at uniform circular motion. We've dealt with this a little in AP Physics 1, and we even talked about this a little in the last unit in just observing circular motion and the acceleration that we can observe. But now we're going to look at what causes that and the forces that are involved in doing this. And so we know from before that the acceleration of an object that's in circular motion is equal to the v squared over r. All right, and that's if we have a constant speed that's moving around. And so let's think about these examples here. If you are a passenger and for a car rounding a curve, so you're in a car, it's rounding a curve, let's say it's curving to the left. The car accelerates towards the center of the curve due to the centripetal force provided by the inward friction on the tires. However, your inertia makes you want to go straight ahead, so you feel friction from your seat, and you may also be pushed against the side of your car, and you feel like there's this force pushing you outward, even though these forces are pushing you inward that keep you in this uniform circular motion. So you think that you are actually being pushed out, but in fact you are being pushed in towards the center of the circle. Now what that feeling of being pushed out is just your inertia wanting to continue that straight path. Now if we look at a space shuttle, the shuttle is kept in orbit around the Earth due to the gravitational pull, and that acts as the centripetal force. The force also acts on every atom in your body and keeps you in orbit around the Earth. You float with no sensation of force, but are subject to centripetal acceleration. So the key with these two examples are one, centripetal force is not its own force. It's a label that we put on a force that's causing the circular motion. So in the car example, it's the friction in your seat and the door pushing on you to keep the circular motion. In the space shuttle, it's gravity that's keeping you in the circular orbit. But in both cases, the sensation that you feel is not necessarily indicative of the actual forces acting on you or the force that's causing the centripetal acceleration. Because when you're orbiting the Earth, you feel like you're in free fall, or you feel like you're in no gravity. However, you actually are experiencing gravity, but because of your tangential initial velocity, you're in that circular orbit and you're always falling towards the Earth. So centripetal force is simple in a way, and yet it's a little tricky in identifying what you will classify the force as centripetal. So if we want to look at the force the force that causes this circular motion, or the centripetal force, we can find that by taking our acceleration and multiplying by the mass, and we get mv squared over r. Okay, and so we're going to use this equation a lot to calculate centripetal force, as long as it's the only force acting in that direction. Typically it will be, but there will be some cases that it doesn't happen. In this case, in this example, we have tension that's actually causing the centripetal force. So the tension is the centripetal force because it's causing the centripetal acceleration. So I want you to pause the video, try this checkpoint here. You have the answers provided, so read through it and check your answers at the bottom. A couple unique situations that we need to look at here is vertical circular motion and going around some banked curves. So a bicycle that goes around a vertical loop is going to experience that centripetal acceleration, but the difference here is we have gravity that comes into play here. And so we have more than just one force that's in the radial direction, is what we call it, the direction of the radius. So let's say we're in a vertical loop. We're going through this loop-de-loop thing. And at the top of the loop, we have the normal force that's going down and the weight of gravity. And that sum is equal to our centripetal force, which is the mv squared over r. Now we're saying these are all negative because we're just assuming that down is negative and up is positive. And so we can solve here for the velocity based upon, what is the minimum velocity we need to keep the circular path? Well, the minimum velocity would be when our normal force decreases down to 0. And so v is just going to be the square root of gr. So we need 5.1 meters per second in this situation of a radius of 2.7 meters, and on Earth with gravity of 9.8, we would need to be going 5.1 meters per second in order to make it to the top of that loop without falling. Another situation that we have is a banked curve, and a lot of times we have turns that are in fact banked so that way we don't have to rely solely on friction, and these equations here are going to help us with these banked curves in finding the angle of the banking or using the angle of the banking to look at the normal force, because our normal force is actually going to be at an angle here.